our notes packet for the 2D forces, here we have now forces that are not going to be at equilibrium. In other words, they're going to be moving. I guess in this case, this one is still in equilibrium. So let's go ahead and read this. We say that we're pulling on a 2.5 kilogram backpack with a force of about 11 newtons. This backpack happens to be traveling at a constant velocity as I pull it. And we measure the angle, and it's directed at about 35 degrees relative to the horizontal. So let's go ahead and draw a force diagram for these forces. Include the following on the force diagram. Go ahead and do that now. Okay, hopefully yours looks like the one that we're going to draw here together now. Well, we have the weight of the backpack. I'm assuming everybody was able to get the weight of the backpack. And we have the applied force. And we said that applied force was at 35 degrees relative to the horizontal. And that applied force is 11 newtons. And I guess technically we can calculate the force, the weight, 2.5 kilograms times 9.8 meters per second squared. And that's 24.5 newtons down. Well, this is in constant velocity. This backpack is moving with a constant velocity, and we know that that is also technically equilibrium. There are zero net forces, and so these forces must balance out then. And so we have a frictional force here, and the frictional force can only be in the opposite direction of motion. So this backpack is moving from the left to the right horizontally, so the frictional force is from the right to the left. Now we also have a normal force. The backpack is resting on the table, and so the table is supplying some normal force. Then we are asked to actually calculate the forces that we don't know, the normal force and the force of friction. Well, in order to do this, we need to make sure that we know the x and y components of everything. And so we have to then calculate the x force applied, Fax, and the force applied, Fay, in the y direction. Go ahead and calculate those now. Okay, I calculated the x component is 9 newtons, and the y component of the applied force is 6.3 newtons. Now let's visually inspect this and see, well, what does the normal force have to be then? Well, here we have 24.5 newtons acting downward, and we have 6.3 newtons acting upward. Well, this backpack isn't just jumping off the table, so the normal then is going to have to balance out whatever the difference is between 24.6 and 6.3. In mathematical terms, the sum of the forces in the y direction has to be equal to 0. That means that Fay plus Fg plus Fn has to be equal to 0. Therefore, 0 equals 6.3 minus 24.5 plus Fn. Fn then is 18.2 newtons. And then we have a balanced system up and down. Now, if we also visually inspect our force diagram, we see we only have two forces in the x direction. We have Fax, and we have the force of friction. And so since this is in equilibrium again, those two forces need to be balanced out. So then the force of friction is going to have to directly equal but the opposite of the applied forces x component. And then we have all the forces calculated. We have the applied force, 11 newtons, the weight, 24.5 newtons, the normal force, 18.2 newtons, and the force of friction, 9.0 newtons. And if you remember, the force of friction is equal to the coefficient of friction times the normal. I guess this is the coefficient of kinetic friction since this is moving. And so if we wanted to calculate the coefficient of kinetic friction, we could do that by taking the force of friction, negative 9.0, or 9.0. I guess we don't need to have a negative. We're just looking at the magnitude, divided by 18.2 newtons. Excuse me. And that's going to get us 0.495. Okay, now let's go to the next problem in this notes packet. We have the Three Stooges. The Three Stooges are dragging the 10-kilogram sled across the frozen lake. Moe pulls with the force M, Larry pulls with the force L, and Curly pulls with the force C. The sled is moving in the X direction. Both Moe and Larry are exerting a force of 10 newtons. What is the magnitude of the force Curly is exerting? Assuming that the friction is negligible, so there's no friction, what's the acceleration of the sled? Now, in this case, we have to add up these three forces with a vector, just with vector addition. Okay, I have brought this over to the smartboard so we can work with it a little bit easier. The problem said that Moe and Larry are each exerting a force of 10 newtons. And it says that the sled is actually moving in the x direction. So that means that the net force, or the resultant force, has to actually be in the x direction. Well, that's kind of strange, because it doesn't look like, from this diagram at least, that will happen. However, if this is to be the case, I'm going to go ahead and erase that again. If the resultant force is in the x direction, we need to remember that the net force, or the resultant force in the y direction, has to then be 0. If it's only going to move in the x direction, the sum of the forces in the y direction has to be 0. So that means that whatever component my is, that must be equal and opposite to cy. Now, you can see why this is not clearly drawn to scale. Because if this was drawn to scale, my and cy would have to be exactly the same. However, we can calculate my. My would be 10 times the sine of 60. Go ahead and calculate that now. And I calculated this to be 8.7 newtons. That means that cy also is 8.7 newtons, just in the other direction. Well, from that then, we can calculate the x components, both of m and of c. Cx would have to be equal to the 8.7 newtons divided by the tangent of 30. Remember that tangent of 30 is equal to opposite 8.7 over adjacent to Cx, and these two can switch places. So here we can calculate Cx. Calculate that. Pause the video if we need to pause the video. And I calculated something that would be right around 6 or 15 newtons. Let's go ahead and do the same for m and find mx. Mx would have to be equal to 10 times the sine or cosine of 60. Go ahead and calculate that now. Pause the video if you need to. We know that cosine of 60 is a half, so that's 5. So the sum of the forces in the x direction is going to be this 5 plus the 10 from Larry plus the 15 in the x direction from Curly. So we have a total of 30 newtons in the x direction. That's sort of the net force. Well, the other part of this problem asks you to calculate then the acceleration. If we know the mass, it's a 10 kilogram sled, then this 30 newtons must be equal to the mass times acceleration, 10 times a. So a, therefore, is 3 meters per second squared. Now, you should do in the worksheet packet for tomorrow problems 1 through 4 in the additional practice problems worksheet. See you tomorrow.